The Earth, over its 4.5 billion year history, has been pummeled by asteroids. Eroded by wind and rain, covered over with flowing lava, wrinkled and gouged by shifts in its crust. Most traces of its distant past have long since been destroyed. But there is a place where clues to the early history of our planet are still largely intact. The Moon. Scientists have been reconstructing its history by scouring its surface, mapping its mountains and craters, and probing its interior regions. What are they learning about our own planet's beginnings? By going back in time to the mysterious birth of the Moon. The space age made possible rockets with enough power to blast humans and their life support systems into orbit. More than 300 manned space flights have shown that humans can live and explore beyond our Earth.
Differentiate me from Dr. Feustel's suit right here, which has red stripes.
None of these missions have done more to shape our connection to the cosmos and define who we are than the fabled flights of Apollo. But not for reasons you might think. We sent astronauts to the Moon as a symbol of confidence in the face of the Great Cold War struggle. Many hoped that would lead to further journeys to Mars and to an age of living in space. Those goals proved too grand in the face of all the preoccupations, turbulence, and change that would crash onto our own planetary shores. Landing on the Moon was a giant leap for mankind. But it's what the astronauts picked up from the lunar surface that may turn out to be Apollo's greatest legacy. When the astronauts of Apollo stepped out of their landing craft, they entered a world draped in fine, sticky dust, strewn with rocks and pocked with craters. They walked and rambled about, picking up rocks, 382 kilograms worth, that they packed for the return flight. Back in Earthbound labs, scientists went to work probing the rocks for clues to one of the most vexing questions in all of science. Where did the Moon come from? The answer promised to shed light on an even grander question. Where did Earth come from? And how did it evolve into the planet we know today? The Apollo rocks have brought us closer to the answer, but basic mysteries still remain. The Moon orbits Earth at an average distance of 384,400 kilometers. It's relatively small, with less than 1% the surface area, 2% the volume, and 1% the mass of Earth. With no atmosphere, temperatures range in Celsius from -233 degrees at night to 123 degrees during the day. As the brightest object in the night sky, the Moon has guided people for millennia by defining the rhythms of life and animating our myths. The nature of the moon began to come into focus 4 centuries ago. Galileo Galilei had heard of an instrument built by Dutch opticians capable of seeing faraway things as though nearby. Galileo, in many ways the first modern scientist, saw this new instrument as a tool to help settle a long-standing question. What was the nature of the heavens, and how did the world of men fit within it? To some philosophers, the moon was a perfect crystalline sphere of divine substance, free of Earth's imperfections. Galileo, with his telescope, saw a more familiar reality. He noted mountains and valleys on the moon, features like those of Earth. Flash forward to the modern age of lunar studies. 1959 saw the first in a fleet of probes launched by the Soviet Union and the United States to shoot close-up pictures, take readings, and crash onto its surface. We learned then just how different the moon is from Earth, with its cratered and desiccated landscapes and lack of a magnetic field. That intensified a debate about the moon's origin that went back centuries. The so-called fission theory, championed by George Howard Darwin, son of Charles Darwin, held that the moon was once part of the Earth, cast off by the rapid spin of its young parent. For proof, look no farther than the Pacific Ocean, a giant hole in the Earth's surface. Then there's the capture theory, which holds that the moon was a wayward object that floated through our solar system and was pulled into orbit by Earth's gravity. A third idea came from the American astronomer Thomas Jefferson Jackson C., also known for his attacks on Einstein's theories and for charges of plagiarism that were leveled at him. He suggested that the moon formed near Earth and gradually fell under its gravitational spell. In that case, the moon should be a mini-Earth, which we now know it's not.
Bypass across the board, Scooter, no action.
The astronauts of Apollo lifted off on a series of missions to get a close-up look at the moon and perhaps settle the debate. Because there's no atmosphere there, the astronauts entered landscapes that are nearly frozen in time. They could scour the lunar surface for evidence of events going back almost to the time of its birth. Indeed, eons of impacts had opened up the moon's interior, leaving a wealth of information strewn about their landing sites. Scientists had already noticed that some large old craters were surrounded by concentric rings. You can see one of the most pronounced examples in this image of the Mare Orientale, captured recently by NASA's Lunar Reconnaissance Orbiter, or LRO. The colors showed differences in elevation. The old view was that the impact had melted the rock below. A newer view held that the impactor had actually splashed down on a molten surface. That gave rise to the radical notion that early in its history, the moon's surface was covered in a vast ocean of magma. When the astronauts arrived, they found relatively light rocks known as anorthosites. Their presence suggested that heavier material had sunk toward the moon's interior, forcing lighter material to the surface. The rocks they brought back were found to be strikingly similar to those on Earth, in part because they share forms of oxygen, called isotopes, that scientists regard as blood types for solar system bodies. Then there was this. The Moon appeared to be completely, utterly dry, with no evidence that water was ever present on its surface. Not long after the last Apollo mission went into the history books, this initial evidence coalesced into a radical new idea, first presented in 1974 by the scientist and artist William Hartmann. His theory of the Moon's formation is played out in this contemporary scenario. Sharing an orbit with Earth was a Mars-sized body called Theia, named for a Titan in Greek myth who gave birth to the moon goddess Selene. Its orbit became unstable, and it headed in Earth's direction. Theia hit at an oblique angle, causing the Earth to spin faster, and debris from both Theia and the Earth to fly into orbit. When the dust settled, the debris began to coalesce in Earth orbit, forming the Moon. By then, volatile compounds like water had evaporated. The Moon, then, comes primarily from the mantles of the Earth and Theia. That's why, overall, the Moon is lighter or less dense than Earth. It has a core of solid iron like Earth, but this core is relatively small compared to ours. From this violent beginning, the Moon gradually cooled, and the magma that lined its surface hardened into a crust. Yet it was still subject to intense bombardment in the chaotic environment of the early solar system. Its surface has been hammered by large impacts at every stage in its history. You can see what a battering the Moon has taken in this global elevation map compiled by the Lunar Reconnaissance Orbiter. The Apollo astronauts encountered a secondary effect of all the impacts. Rocks formed in the crucible of widespread volcanism. On Earth, volcanic eruptions are often powered by water, heated and pressurized by friction from the movement of immense tectonic plates. Neither factor exists on the Moon. Instead, lunar volcanoes are tied to impacts, forceful enough to melt the surface and release material from the hot interior. In the lower gravity of the Moon, volcanic eruptions would have splattered high above the landscape. Molten rock then flowed out in thin, smooth layers that reached far from its source. That's how the mare regions, that cover about 1/6 of the entire lunar surface, were formed. These immense volcanic basins are thought to date back to a period of large and violent impacts from 3 to 4 billion years ago. The materials brought up by these impacts are made up of heavier compounds that would have initially sunk into the magma ocean. Scientists have also detected volcanic residues in recent impacts that have been imaged by LRO cameras. This is the Aristarchus Plateau, with a mysterious channel cut by flowing lava and punctuated by two immense craters. One was created by an impact just 450 million years ago. Along its walls are blocks of rock from the lunar crust that fragmented in the impact. Scientists detected volcanic glass-like deposits that are the legacy of ancient eruptions. Then there's the strange landscape of the Tycho crater from an impact about 100 million years ago. Its central peak, rising 2 kilometers above the crater floor, may be material blasted out by the impact. The same is true for a 120-meter wide boulder that sits on the summit. Around it and on it, scientists see evidence of rock that was melted in the heat of the impact itself. Since its birth, the Moon has exerted a constant and powerful influence on Earth. Gravitational drag from the Moon slows Earth's rotation by 2.3 milliseconds per century, while causing the Moon to drift away at a rate of 3.8 centimeters per year. The Moon's tidal pull acts to stabilize Earth's rotation about its axis, and the tides help promote the formation of ocean currents that shape our climate. To think that the root of this intimate relationship between Earth and the Moon stems from a violent collision so long ago. However, the giant impact theory is not universally accepted. For one thing, there's the issue of water. The dryness of the Moon is consistent with the giant impact theory, which predicts that water and other volatile compounds would have evaporated out of the lunar debris cloud. But the Moon may not be so dry after all. In 1998, the unmanned lunar prospector began an ambitious mission to map the lunar surface with an instrument called a gamma-ray spectrometer. The data showed that hydrogen is spread widely across the poles of the Moon. If it's from ice, millions of tons of water could well be embedded in the soil there. It turns out there are places where water can exist on the Moon, where the sun never shines. Polar craters forever in shadow could shelter significant quantities of ice against solar radiation. Prospecting for ice, the L-Cross probe arrived at the Moon in 2009 aboard the Lunar Reconnaissance Orbiter, on a collision course with the 97-kilometer-wide Cabeus crater at the South Pole. Seconds after it slammed into the crater, a trailing probe detected a tenuous cloud rising up from the crater. In the cloud was a mix of carbon monoxide, ammonia, methane, and more. 5.6% of the crater floor is water ice, a higher concentration than some areas on Earth. The presence of water is good news for explorers who dream of one day spending quality time on the Moon. But how did it get there? It might have been delivered by comets striking the Moon over the eons. There's another explanation, one that emerged from rocks gathered by the Apollo astronauts. The samples are graced with tiny glassy globules, minerals melted in the crucible of lunar volcanism. Analyzing these Apollo rocks with new techniques several teams of scientists have found a compound called hydroxyl. It's H2O with only one H, and could be turned into water, say, for a moon base. Much of what the moon had was likely lost to space from impacts. Tiny residues might remain in polar craters. The rest, still locked up inside the moon, might be enough to cover its surface in a layer of water 1 meter deep. Does the presence of water inside the moon send us back to square one on its formation? It might not, if it had been carried in by comets in the moon's early days. One new study suggests that the giant impact scenario is more complex than we thought. It holds that another, much smaller body formed alongside the moon and eventually merged with it. The impact literally rearranged the moon's interior, pushing molten magma onto the near side while adding an extra layer of crust to the far side. That explains the lopsided topography of the moon, the dark lava basins on the near side, and the highlands of the far side. Human geologists with a network of seismographs could confirm this idea. The next best thing is a mission called GRAIL, a pair of spacecraft orbiting the moon in unison. Such a mission has already performed a kind of planetary CAT scan of Earth. By measuring subtle changes in the distance between the craft, scientists discerned variations in Earth's gravity. The data resulted in a map of groundwater all around the planet. Flying around the moon, the GRAIL pair could provide new details about the size and composition of the moon's core, adding support for the giant impact theory, or sending science in a whole new direction. The intimate connection between the Earth and the Moon appears to trace back to their earliest times. If that's true, then the formation of this desolate world can tell us about our own. A blue-green world with a companion reflective enough to light up the night.